Right, so we're gonna, yep, so this looks good to us now.
Perfect.
All right, thank you so much. I apologize for the inconvenience. All right. So good afternoon, everyone. I'm Danny Lim, a graduate from the University of California, Santa Barbara. I'm excited to share with you a research project that I had the privilege of contributing to. Today, I will talk about the intriguing phenomenon of serial dependence and its connections to the quality of spatial work memory. Thank you for joining today, and yeah. So in our daily lives, our perception of the present is influenced by both past experience and incoming sensory information, creating a continuous sense of time. This integration of outdated input and current stimuli allows us to anticipate the future and maintain the temporal continuity. One interesting aspect of this phenomenon is known as serial dependence, where our perception of an event is pulled towards recently viewed stimuli. To illustrate this concept, imagine driving on a sunny day when suddenly fog rolls in, making it hard to navigate the road. In such situation, we often rely on information encoded in our recent past, such as the curvature of the road. By drawing upon this previously encoded information, we can safely navigate challenging conditions like foggy weather. So serial dependence, therefore, helps us maintain a stable representation of our environment over time. In our study, we aim to answer two main questions. Does attractive serial dependence occur in a memory-guided Saccade task? And what is the role of memory quality in serial dependence? Throughout this presentation, I will provide you with the answers to these questions, building a comprehensive understanding of this phenomenon. So let's begin by discussing the memory-guided Saccade task we employ for our research. As you can see on the right, participants were asked to perform a spatial working memory task using an eye tracker and a monitor. In this task, they were instructed to fixate on the center with their head fixed. While they're still fixated on the center, a colored dot appears briefly in the periphery of a circle and then disappear. After a short delay, when the response cue appeared at the center, participants had to recall the location of the target they saw in their periphery visions, making saccadic eye movements based on their memory. They were provided with feedbacks when a target dot reappeared, allowing them to adjust their eye movements to the exact location of the target. The experiment continued with the participants fixating back on the center of the circle. So you may be wondering how we examine serial dependence in this Saccade task. Well, as the trial progressed, the reported location of the dot could be influenced by the location of the dot in the previous trial. To understand this, it is important to focus on two key variables: relative target difference and response error. The relative target difference indicates the previous target location relative to the current trial's target location in terms of polar angle. So let's consider an example to understand these variables. In the previous trial, a blue dot was located at a 45-degree angle. And in the current trial, a red dot appeared at a 100-degree angle. By calculating the relative target difference, we obtain a value of -55 degrees. Response errors represent the reported location relative to the target location within the trial, also in polar angle. So when reporting the location based on memory, participants could either exhibit bias or no bias at all. The faded blue colored dot represents the previous trial's target location. So if the reported location aligned exactly with the target as indicated by the green light, it means that there was no bias, meaning no effect from the previous trial. However, if the reported location is slightly closer to the previous trial's target location, we refer to it as the attractive serial dependence. Assuming the serial dependence occurred in the scenario as indicated by the orange arrow, we can calculate the response error using the provided formula. In this case, it'll be -5 degrees. You may notice that both the relative target difference and the response error have the same negative signs. So if both values have the same sign, we observe the phenomenon of an attractive bias, indicating that participants are reporting their remembered location slightly closer to the previously target location. In our first study, we aim to replicate the serial dependence effect by employing the memory-guided Saccade task. The scheme on the left is essentially the same as I described earlier. During each trial, participants were instructed to fixate on the center while trying to remember the location of a randomly appearing colored dot. After the dot disappeared, a delay period followed, and when a response cue appeared at the center, participants reported the remembered location by making saccadic eye movements. The actual target dot reappeared shortly after to provide them with feedbacks. So analyzing the participants' data, we plotted the distribution of response error corresponding to the relative target location for each trial for an exemplar subject. So in the absence of bias, the distribution of response errors will be evenly flat, regardless of the relative target difference. However, if there is a random bias, the distribution would appear random. And when we plot the entire data set, we observe that there are more responses in the quartile where the sign of the response error matches the sign of the relative target difference, indicated with the red boxes. To further analyze zero dependence, we fitted derivative of Gaussian curve known as DOG curve shown by the red line. The dark blue line indicates the moving average of error, and the shaded blue indicates the standard error of means. On the right, examining all participants' data, the DOG curve fitting consistently demonstrated an attractive bias, supporting the occurrence of zero dependence. So earlier, I used the analog of driving into fog to demonstrate how zero dependence can bias our perception towards past experience. In that scenario, our ability to navigate the road curvature would be attractively biased towards the information from when the weather was still sunny, giving more weight to the past observation. So now let's explore the reverse situation, driving out of fog into sunny weather. As we emerge from the fog and regain a clear sight, the information about the road curvature that we retained while in the fog may not be as useful or informative. This is especially true if our memory of the road curvature is poor. In such cases, we would rely less on the previously presented information and place more emphasis on the current visual cues provided by the clear weather condition. This idea is supported by the Bergen and Jihe's 2019 paper, which suggests the weight given to the current and previous information is determined by its relative quality, and placing more weight on previous information leads to a zero dependence bias. So in study 2, we aim to investigate how this difference in the quality of working memory influenced the magnitude of zero dependence. We employed the same memory guided Saccade task as in the first study. In this experiment, we introduced an induced trial that always preceded a prop trial. Thus, the first trial was the induced trial, the second trial was the prop trial. Consequently, odd-numbered trials were induced trial, and even-numbered trials were the prop trials. The induced trial had 3 different conditions. The R1 condition involved only one target, as depicted on the left. The other 2 conditions displayed in the middle on the right included 2 targets presented in different colors. In the R2 random conditions, the participants were asked to recall the specific target location that matched the color of the response cue at the center. In the R2 best condition, participants were instructed to report the location of either one of the 2 targets that they felt they remembered the best. By introducing multiple conditions in the induced trials for study 2, we were able to differentiate the level of memory quality before the prop trial. After each induced trial, a prop trial followed, which was essentially the same as the R1 condition. By differentiating the working memory quality using the induced trial, we aim to measure the magnitude of zero dependence based on participants' performance in the prop trial. So we first examined whether zero dependence also occurred in study 2. The exemplar subject data depicted here confirms the occurrence of zero dependence in study 2 as well. It's shown by the DOG curve. So yes. Step 2, next we examine whether we successfully differentiated the level of memory quality in the induced trial. As we can observe in the plot, the response error for the R1 was the lowest, indicating the best memory performance when participants were asked to remember only one item compared to 2 items. Therefore, we can conclude that there is a difference in memory quality in the induced trial. Now that we know zero dependence occurs in study 2 and there is a memory quality difference in the induced trial, we can discuss our expectations. Based on our hypothesis, we expect the magnitude of zero dependence to vary depending on the quality of the previous trial's working memory. If our hypothesis is supported, we will observe a pattern similar to the one depicted on the right, where the magnitude of zero dependence is greater when the memory quality is better, resulting in lower response error. So the R1 condition would show the strongest zero dependence, while the R2 random condition would exhibit the weakest zero dependence due to its lowest accuracy in response error. So step 3, in this figure, we have plotted all the DOG fitting curves for each condition. So the blue line represents the R1 condition where there is only one target, and while the red line represents the R2 random conditions and yellow line represents the R2 best conditions. The magnitude of zero dependence is measured by the height of the curve. So we plotted the zero dependence amplitude for each conditions. And surprisingly, there was no significant difference in serodependence magnitude across task conditions. However, the qualitative result aligned with our prediction, as you see. One possible explanation for this lack of significance could be that within trial variation in memory quality of individual items were not sufficiently large to impact the biases on the subsequent trials. Due to the study design, the size of the induced trials were relatively small, which accounted for only 1/3 of the prop trial size. So therefore, opportunities for improvement exist for future studies. So in this study, we aim to address two main questions. Firstly, we investigated whether serodependence occurs in a memory-guided Saccade test. And the DOG curve fitting in both study 1 and study 2 provided evidence supporting its occurrence. Then we explored the role of memory quality in serodependence. Although we did not find significant difference in serodependence magnitude across task conditions, the qualitative analysis suggests the magnitude of serodependence is greater when the memory quality from the previous trial is more accurate. And investigating intriguing phenomena like serodependence is crucial for enhancing our understanding of working memory, and look forward to further explore such phenomena in my future. Before concluding the presentation, I would like to express my keen interest in pursuing a PhD program in this captivating field for the upcoming term. So I welcome any opportunities related to potential doctoral position. So please feel free to reach out to me. Thank you all for listening to my presentation, and I look forward to any questions you may have. Thank you.
All right. Thank you. That was great. All right, so let's do a couple minutes for questions specifically to this